All right, let us continue the discussion of ergodic actions of groups. And then later we will apply these techniques for the proof of most of rigidity theorem. So let me recall that ergodicity, so ergodic actions of groups, and we recall that this means that, so recall that H X ergodically on the space X. I think that we will assume for now that we have a probability measure on X, so where X A mu is the probability space. Yeah. So it is a space with probability measure. In fact, it is enough to assume that it is a finite measure, then you can normalize it, right? Okay, so then recall that Hx, okay, Hx where, comma, ergodically, or the action, okay, so recall that the action is called ergodic. The action H and X, and this is a group, is called ergodic if, well, we can reformulate it in the sense of functions, but I will say that if for every H in, okay, so first of all, if H is measure preserving, right? So if it is measure preserving, and for every H in H, the invariance means that either, so if the set is invariant under H, it is either zero measure or the full measure, right? So, and for every H in H, HU is U implies that measure of U is zero, or the measure of X minus U is zero, okay? Yeah. And yeah, so this can be reformulated in the sense of, so this is ergodic. This is equivalent to the fact that every H invariant measurable function is constant almost everywhere. Yeah. This is equivalent to the following. Every H invariant measurable function on X is constant, okay, mu almost everywhere, right? Then actually there is the following nice sequence of the action H being ergodic. So let me suggest it as a lemma. the action of the group H, of a group H on X is ergodic. If the action is ergodic, then almost every orbit of H is dense. Well, technically it should be dense in the support of the measure mu. So then almost every orbit of H is dense in the support of this measure. I think I'm not going to give all the details. I will just leave a hint. And okay, the hint is, I guess, the following. So the first, observe that if, okay, well, so assume that the support of measure mu is the entire X, right? So which means that it is not equal on it. So the measure mu is not equal to 0 on the, right? So the subset of, you do not have a like large subsets of X where the measure is 0, right? So it's not 0 on every non-empty measurable set in from the signal algebra. Yeah, so you cannot, so like basically it's just enough to switch from, I mean, you can just start from switching from X to the support of mu, and then, yeah, so there's no difference. But yeah, but technically you can have a measure, right, which is, I don't know, something like that. So it's 0 everywhere except some parts. So if you start with the real line, you can, or a large segment, you can choose a measure which has some density such that it is not 0 only on some subsegment of your segment or something like that. So to avoid that, you just change X and then you work with the support of measure being the entire space X. Okay, then if, so this is the first, then, okay, if the measure, okay, yeah, if the measure of U is not, right, if the measure of some space U, oh, sorry, of some sets, some set U is not 0, then the measure of HU is definitely not 0 as well, right? Since H is measure preserving, so it's not 0. Moreover, for any HU, sorry, for any U, HU is already H invariant. So if mu, then mu of HU is not 0. And since U prime being HU is H invariant, so U prime is H invariant. Let's apply the definition. What does it mean about the measure of U prime? It's either 0 or the complement is 0, right? But we already showed that due to H invariance, it's not 0, right? So since now this image of U under H is H invariant, and we started with a set of non-zero measure, we obtain, so we have that the measure of X minus U prime is 0, right? Well, in fact, we can show that actually, since I chose like probability measure, we can say that the measure of U prime is equal to 1. If I'm not mistaken, this lemma holds for non-probability measures as well. But for probability measures, it's just a bit simpler since it remains to consider, I guess, okay, then the second hint, well, the first part is pretty like actually already well detailed. The second part is not detailed, but can consider, so the indicator function, I don't know how it's called, like indicator of any H invariant set is an H invariant measurable function, right? So I just leave it as an exercise to finish the slam. So, but let me again concentrate on the statement. It's pretty nice. So the ergodic action means that almost every orbit is dense in the support of the measure. Again, our measures will mostly be pretty nice measures like Haar measures. So the support of this measure is the entire space X. And this means that the actions of our groups mostly will have dense orbits. All right, this was the first lemma. Yeah, recording is in progress. So the second lemma we will certainly use is the following. Okay, I think that let G be, in fact, it can be any locally compact topological group, but let it be a Lie group, okay? Let G be a Lie group. And suppose that I have two closed subgroups. And H1, H2, closed subgroups. This includes also discrete subgroups of Lie groups, right? Since these are definitely closed, and well, in fact, discrete subgroups of Lie groups are just Lie groups of dimension 0, right? So here I will write includes discrete subgroups of the groups. Then the action of H1 on the quotient in the homogeneous space G mod H2 is ergodic. If and only if the action of H2 on G mod H1 is ergodic. So you can change, and again, this will be essentially used in the proof of the most of rigidity. So we will prove, well, basically I will give you one of the most important theorems from this, like theory of, okay, I would say one of the fundamental theorems in the theory of ergodic actions of groups, of discrete groups. And this trick, this lemma, will allow to like switch from one action to another. What is, okay, again, I want to like start a sketch of proof of the most of rigidity theorem as soon as possible, so I will omit the proof of this lemma, but in fact, you really don't need that much of like background to prove this lemma as well. I think it's just based on, okay, it's mostly based on the fact that okay, I think that mostly is based on the fact that measurable functions are constant almost everywhere. And in fact, you just need to like basically draw it, to think of a diagram and coset and cosets. So like think of G, here you have G mod H2, and here you have G mod H1. So just think how to pass from here to G and then to G mod H2. I think that you might probably need to think of maybe left and right cosets of this G mod H1 and G mod H2 to make it work. Yeah, but okay. So what is really very important for us is the following theorem, and this is called the Moore ergodicity theorem. Moore ergodicity theorem. I will formulate it. I think I will formulate it in the following setting. So let G well, again, it's two in quite a broad setting, but I can state it. Okay, I can state it as follows. So let G be a semi-simple Lie group. So like we can assume that it's like the product of some simple vectors, right? It's a let it be a connected semi-simple Lie group. Okay, with trivial center. And let us assume that it's and without complex factors, but well, in fact, we don't really need it, but center and without compact factors. In fact, we can think of just simple Lie groups, since in our case, we will apply this to the case when G is S, well, okay, it's something like POD1, which is with the connected component of POD1, right? And then it's just going to be, as a Lie group, it's going to be just a simple Lie group. So it cannot be decomposed into the product, definitely. And yeah, and let H be just any closed non-compact subgroup. So, if gamma is a lattice and H closed non-compact, then the gamma action on, so the action of, then the action of H on G mod gamma is ergodic. Sorry, and then by this lemma, I can switch, right? Then the action of gamma on G mod H is also ergodic due to the previous lemma. All right. Yeah, I mean, ideally, I would prefer to prove this theorem, and generally, okay, at least to sketch the proof. This is based on the following, on the famous Howe-Moore vanishing theorem, or theorem about like vanishing coefficients. This is related to, so one needs to consider unitary representations of the Lie group G into some Hilbert spaces, and then work with the basically to analyze the invariant vectors under such representations. So you asked me about representation theory. Here it's really the proof of this theorem pretty much deals with such representations. So but unfortunately we probably do not have time for this. But yeah, this theorem itself is just very, very nice, and in fact its proof is beautiful. Okay, so now I'm going to describe a couple of cases when, so maybe let us consider some specific cases. Okay, like I would say some examples. And in fact, these examples like actually are important for the proof of the most of rigidity theorem. So the first example is the following. I can take G be just PSL to R, right, which is the orientation preserving isometry group of H2, and gamma, okay, gamma lattice in PSL to R. So for instance, it can be PSL to Z or something. And I also want to say the following. So M, okay, but assume that it is torsion free. So it's not PSL to Z, but after finite indexes, I can always pass a torsion free subgroup to torsion free subgroup. So assume that it's lattice and torsion free. Then S of, which is the quotient of H2 and gamma by gamma, is a surface, right? Is a hyperbolic surface. And the quotient G mod gamma, in fact, can be identified. So the quotient G mod gamma can be identified with the unit tangent bundle to the surface S. By the unit, I mean that we have tangent spaces, right? We have tangent bundle to the surface S. So I have a tangent space, right? And yeah, I want to consider only the vectors of unit norm, right? So my V belongs to TPS, right? But the normalization of the by its norm, well, with respect to the metric on S, I don't know, I will write something like that, already belongs to T1 PS. If I'm not mistaken, you can always identify Gmod gamma with T1S. So the claim is that one can identify this quotient with this tangent, unit tangent bundle. Okay, then I can take following subgroup in G. I can take a one parameter. So there is this so-called, okay, this is the basically the Hopf theorem. Is that if GT is a one parameter subgroup, so for instance, it can be a geodesic flow or a horocyclic flow. So let GT be a one parameter subgroup. Then the action of GT on Gmod gamma is ergodic. As GT, one can choose a horocyclic flow, which is basically generated by the matrices 1T01, right? So it's a special case horocyclic flow. You can act by this one parameter subgroup, right? Or one can construct a geodesic flow. It is usually denoted by gamma T, and it basically works as follows. For every point P and any direction V, we kind of do the translation along the unique geodesic from P, passing from starting from P along the vector V, and we do the translation along the parameter T fixed here, right? In fact, I think that one can also describe it in the sense of matrices. So probably it's going to be just homothesis, right? It's probably going to be just diagonal matrices, e to the power of t and e to the power of minus t, the exponent of minus t. I'm not sure, but probably, yeah. And the second, okay, this was the first example. But the second example is going to be on the next board since it's a pretty big one. Okay. Example number 2 is, in fact, precisely what we will need. So let G be the group of, okay, in fact, I can assume that it's the isometry group. Or I can say that it's the connected component of the isometry group. So let it be just isom HD, right? But I think that if I choose the isometry, okay, orientation preserving isometry group, then in my notation, okay, in notation of this course, it can be also identified with the group of conformal transformations, conformal automorphisms of the boundary. So this boundary being just SD minus 1, right? Okay, let gamma be a lattice. And I also want to fix the point on the boundary. Okay, which is our D minus 1 dimensional sphere. Let us consider the group. Consider the group H being just GP. And in fact, this group GP is the group of isometries that preserve the point P. In fact, I might have said something wrong last time when I said that it's going to be the isometry group of the Euclidean space, but it doesn't, but it includes not only parabolic isometries, right? This group also preserves, so for instance, if it is, I can also, so say if P is 0, right, it also contains all similarities, all just homotheties, right, all, I need to check, I need basically to take all the, or maybe I should consider the, let me think, what's easier? Maybe if P is infinity, I need also to take all the vertical half-lines passing through P and all hyperbolic elements whose axes are these vertical half-lines, right? So all hyperbolic elements whose axis contain P also lie in this stabilizer. So in fact, if I remove the point P, I obtain the Euclidean D minus 1 dimensional space, right? If I remove it from the boundary. And it naturally acts on this D minus 1 dimensional space as the group of Euclidean similarities. So GP can be, this group can be identified. So this group can be identified with the group of Euclidean similarities of the so of the Euclidean space of dimension d minus 1. And in fact, it is the group which looks like the product of OD minus 1 and RD. Okay, this group is, okay, sorry, yeah, I will write. It is just the product, since I started from orientation preserving isometries, right? I also need to choose only orientation preserving similarities. So it gives me SO d minus 1 product RD. And yeah, this is just my picture. So it's certainly larger than the group of orientation preserving Euclidean isometries, which is SOD minus 1 times RD minus 1. Yeah. So here I just recall that isom ED minus 1 is SOD minus 1 times RD minus 1. In fact, this is somehow, it follows from the polar decomposition, but it is there is a more deep result from the group theory, is the Iwasawa decomposition. You can decompose any Lie group G into the group components K, A, N, and K here is going to be this compact subgroup of, I think, rotations around one axis. Then you will have probably, yeah, translations, and I guess the similarities gives you just the action by R star, and this can be identified with just this product. Yeah, but I'm not sure that I can recover all the details like out of my head, but approximately this follows from the Iwasawa decomposition. All right, so in fact, this group GP is a famous so-called parabolic minimal parabolic subgroup. So in fact, this GP is isomorphic to, so it's a minimal parabolic subgroup. Well, it is just like, again, it's just some fun fact, parabolic subgroup. Okay, what we now need is that the action of this group GP is ergodic on G mod gamma, right? The action of GP on G mod gamma is ergodic by Moore ergodicity, right? This implies that the action of gamma on G mod GP is ergodic. But what is the action, what is the quotient G mod GP? G, let me remind the basics of the homogeneous spaces. G acts transitively on SD minus 1, right? So the stabilizer, the quotient of the transitive group of diffeomorphisms by the stabilizer gives me just our manifold SD minus 1, right? So then by lemma, okay, it's like lemma 2, right? Number 2. We have that gamma x on G mod GP is ergodic. In this case, G mod GP is precisely the ideal boundary, right? This is SD minus 1, which is the ideal boundary of HD, and which coincides also with the limit set, right? And this is the limit set of gamma, since gamma is a lattice. And I will just remind, since G acts on SD minus 1 transitively, and GP is and P is this, so GP is the stabilizer, right, of this point. Okay, so this is a very nice consequence of the Moore ergodicity theory, right? So we have that actually this action of a lattice on the boundary, right, on the ideal boundary of this hyperbolic space is ergodic, which means that almost every orbit is dense, and which in particular means that every, so yeah, what is the measure on G mod gamma? It is just precisely the Haar measure, right? So in fact, this implies that if I like pass to this quotient, I get the following: almost every measurable function on the, so okay, almost every, I should say almost every, every gamma invariant function is constant almost everywhere on the sphere. And this consequence about constant function we are going to use. So in fact, yeah, so the sketch of proof of most of rigidity will be discussed after the break, but this fact is very important. Okay, yeah, let's make a 10-minute break. All right, so let us continue. Yeah, by the way, so after these questions, I recall that probably Hopf theorem refers only to geodesic flows. In fact, I'm not sure, unfortunately, about the state of the art, but as I remember, Hopf proves actually ergodicity of geodesic flows on every hyperbolic, actually just on every probably closed hyperbolic manifold or hyperbolic manifold of finite volume. And then Anosov proved the ergodicity of geodesic flows on already non-constant negatively curved at least surfaces, and then later it was proved on manifolds. There is also a question about horocycles and horocyclic flows and their ergodicity. I suggest to move this discussion to outside lectures. I am still pretty sure that this statement should be true, but yeah, indeed, we have some questions how to prove ergodicity of horocyclic flows. Yeah, but indeed, it, like as to me, it should follow from just Ratner's theorem, since these are unipotent elements, and for unipotent one parameter subgroups, it's just the it should be the consequence of the of Ratner's theorems, I think. Okay, Ratner states that every orbit is either dense or discrete, but I still don't see why Moore ergodicity theorem doesn't apply. It probably should. It's a one parameter subgroup. It's non-compact. Yeah, and it's closed. So yeah, I mean, it's just very simple. It's a simple Lie group. So I mean, it should be true. So let us just separately analyze four cyclic flows. So our plan for now is to sketch the proof of the most of rigidity, and this is going to be hard. Okay, so I have the following scheme. So again, let me just recall what we're going to prove. We have two hyperbolic manifolds. We have compact hyperbolic manifolds, M1 being equal to HD mod gamma 1, and M2 being equal to HD mod gamma 2. So that is, lattices are uniform. Gamma 1 and gamma 2 are uniform lattices. In the Lie group G, which is the isometry group of the hyperbolic space, and it can be identified with P of D1. All right, so we want to prove in fact the following chain of implications. So we want to prove that so if I don't know, phi is an isomorphism, right, of gamma 1 to gamma 2. So let me remind that, okay, for simplicity, these are manifolds, right? We have compact manifolds. So this is pi 1 of M1, and this is pi 1 of M2. So then The first implies that there exists a homotopy from M1 to M2. I have some notations, but okay, so it gives the homotopy, smooth homotopy F from M1 to M2. Let me try to use different colors. Oh, by the way, I didn't switch to the board. Yeah, sorry. So again, yeah, the statement of the most rigidity theorem. Here, I have two compact manifolds. I didn't write the dimension is greater than 2. So I should D is greater than 2. This is very important. So I have two uniform lattices in POD1. We want to prove the following chain of implications. So I start from an abstract group isomorphism of gamma 1 and gamma 2. Then I want to prove that there exists a smooth homotopy. Smooth homotopy. And then the next is that I want to show that it gives me homeomorphism, right? So then this implies the homeomorphism. And the last is isometry. So this is formula and this is isometry, right? So this is our goal. Okay, now there will be a pretty long sequence of steps. The scheme is the following. So we start with the scheme. Again, I just repeat that we start from phi to gamma 1, gamma 2, it is an iso, right? And the first step is to get this smooth homotopy. But I think I can shortly say the following. I have to first of all, these are two. So in fact, these are two spherical manifolds. So it gives me a homotopy since. Okay, so I will denote this again. This is the homotopy. And step number 1 is basically homotopy can be obtained. Homotopy obtained due to MJ being a spherical. There is the so for a spherical manifolds there is like a standard fact that and so a group isomorphism of their fundamental groups allows you to lift to actually just gamma equivariant homotopy, and then use Whitney approximation theorem So if your initial homotopy is not smooth, you can approximate it by smooth homotopy, right? So this is obtained due to MJ's being a spherical plus Whitney approximation theorem. Whitney approximation theorem is a standard fact from like differential topology that if you have a homotopy of two smooth manifolds and our manifolds are certainly smooth, right? Then you can approximate it by smooth homotopies. Okay, so this was step number 1. The next step number 2 is, okay, in my plan it is the following. I want to lift it so it extends to the so-called pseudo-isometry from HD to HD. So I have now F tilde, which is already from HD to HD. And it turns out that this map can be constructed as a so-called pseudo-isometry. We will discuss this step in some details. Okay, the step number 3. So step number 3 gives me that I can consider the boundary map, and the boundary map is the homeomorphism. So consider, so from pseudo-isometries, we pass to the boundary map, and we will study the properties of boundary maps. So let me say that this is a boundary map. And in fact, this boundary map is going to be so-called K quasi-conformal boundary map. And this map is K quasi-conformal. All right. Then I need step number 4. Yeah, it's a long one. Well, not that long one, but it's still pretty hard. Yeah. So step number 4 is that this boundary map is differentiable almost everywhere. So the next df tilde is differentiable almost everywhere. It's actually a pretty delicate analytic result. It follows from the fact that it's quasi-conformal, and this is a theorem that was proved really long ago, probably in the very beginning of the 20th century. Interestingly, it's not involved in the standard calculus for mathematical analysis courses and undergrad courses. It's really more complicated than classical such theorems. We are not going to prove and just even sketch the proof of this theorem. It's pretty a long one in itself. So the next step Yes, and actually here I want to highlight following. So it's almost, it's differentiable almost everywhere on, right, as d minus 1, where d minus 1, due to the condition that d is greater than 2, right, d minus 1 is thus greater, strictly greater than 1. It doesn't work for d minus 1, doesn't, so it's not true on just the circle. And here, where is this entire scheme is, it's one of a few places where this entire scheme fails to work. Yeah. So there is no rigidity in dimension 2, as we know, and it's interesting. It's just interesting to remark where this proof fails. So, and here I will say that doesn't work on S1, right? So this step, when that is when d is equal to 2, right? Okay, then step number 5. Step number 5 is that the differential of this boundary map is also K-quasi-conformal. Okay, then step number 6 is that gamma x ergodically, right? And this would imply that k is actually equal, this parameter k is equal to 1. Okay, basically the step number 6 is very important. K is equal to 1 almost everywhere. And here we use this ergodicity. Moore ergodicity, and in fact this Moore ergodicity and all this ergodic techniques will be used, in fact, a few times just for proving, like basically it will be used like a couple of times to get to the step 6. So Moore ergodicity plus my ergodic lemmas, right? Ergodic lemmas. This is for the proof of step 6. But if this is quasi-conformal with this parameter 1, then this implies that they both are just conformal. So this implies then it is basically by definition of quasi-conformality. I will give you the definition of quasi-conformality. So this implies that both d of tilde and the boundary map itself are just conformal. So that is that d of tilde belongs to the conformal map of the sphere. But if it is conformal map, then it means that right, if I started with some pseudo-isometry, which is conformal on the boundary, it means that on the boundary is like, roughly speaking, generated by inversions of with respect to temper spheres, right? But then it means that it implies that the map F tilde itself is just an isometry. F tilde is an isometry of HD. So this is the scheme, okay? Hmm? Yes, yes. Yes, you still need to like, well, it means that you need to deformate it a little bit, but yeah, you need to make some deformation to make it still to be in isometry. Yeah. All right. So let me try to say something about pseudo-isometries and quasi-isometries first. And this is probably the first like step. So step number one, I would say it's like roughly explained. Okay. Again, unfortunately, I really do not have time. So when I analyzed this, the proof of most of rigidity last time, it like took me probably around 3 lectures to give more details of for each step, but still I skipped really a lot of things. Okay. Great. So step number 2, passing from smooth homotopy to pseudo-isometry. First of all, let me define pseudo-isometries and say what are quasi-isometries, just since it's just 1.5. Okay, so by definition, if I have 2 metric spaces, then pseudo-isometry will F from X to Y. X and Y are metric spaces. So it's basically a pair X and the metric. And here I also have a metric is pseudo-isometry, or sometimes just C epsilon pseudo-isometry. Okay, we'll just write pseudo-isometry. If there exist constants C and epsilon, if there is C greater than epsilon, sorry, greater than 0, epsilon greater than 0, such that for every such that I have the following, such that 1 over C multiplied by the distance between the points A and B minus epsilon is less than or equal to the distance between the images. So should be between f of A, f of B. So the metric is already rho y. And this is bounded from above by C multiplied by for X between A and B. This is a pseudo-isometry. So the first remark is, but it's for quasi-isometries plus epsilon. For pseudo-isometries, it's without. And this is, yeah, this is important. This definition of pseudo-isometries gives us the following. So first of all, if epsilon is, okay, well, like first of all, this bound implies that this is a Lipschitz map, right? For quasi-isometries, indeed, I will need plus this constant. And generally speaking, quasi-isometries, okay, as far as I know, they are not always Lipschitz maps. So they can be something more. Yes, exactly. Lipschitz maps are continuous. Quasi-isometries, so pseudo-isometries are also continuous. Yeah, exactly. So generally, yeah, quasi-isometries are not. I will just give quasi-isometric definition right now. And so if epsilon is 0, for instance, then definitely it's a B-Lipschitz map. And if in addition C is equal to 1, then I just get an isometry, right? Since then this guy will be equal to this and will be equal to rho X, right? The distance between the points will be equal to the distance between the images. So such that this holds for every A and B in X, right? And indeed, I need to say that a pseudo-isometry, so it's a bit more strict definition, but this is going to be a quasi-isometry. Okay, and sometimes the parameters are involved, C1, C2. Quasi-isometry, usually called UI. Okay, now I will give, there is some like tricky thing. It's quasi-isometric embedding. And if it has a quasi-isometric inverse, it's called to be a quasi-isometry. So I will give the definition of quasi-isometry from like all together. If there exists C1 greater than 0, C2. Okay, technically this is greater or equal than 0, right? So such that 1 over C1 multiplied by the distance between the points A and B minus C2 is less than or equal to the distance between the images f of A, f of B, and this is less than or equal to C1 for X plus AB plus C2. Okay. Yes, for any A and B in X. And for any, I think I will say it, that for every point okay, I will say it right here. And for every point y in my space, capital Y, there exists in X such that the distance between f of x and the y is less than or equal to C2, right? So in fact, this second definition is equivalent to the following. So let me, without the second condition, it is the so-called quasi-isometric embedding. So generally speaking, you may have quasi-isometric embedding, but then we say that there exists a quasi-isometric inverse, right? A quasi-isometric inverse, if there exists another map from y to x, such that it's also a quasi-isometric embedding. And what do I need for being this quasi-inverse? I want to, I want like the composition of these two maps to be like roughly the identity, right? And in fact, this is equivalent to this condition. One can show that this is equivalent to this condition. So if it is really quasi-isometry, then we also have a quasi-isometric inverse, which is also mapped. So it makes this definition makes the set of quasi-isometries actually to form a group with respect to just standard composition of maps, right? And okay, so then I think I have the following fact. I just wanted to mention, okay, let me use this board. So I wanted just to mention a few like fun facts about that. So okay, just wait, innovation. Quasi isometries of X is simply the set of quasi-isometric maps from X to itself, right? And it is interesting that the following is true, right? We remember that the isometry group of HD, okay, in my notation, oh, I think I am partially confused that conformal here, conformality actually includes here. So I use this notation for conformal maps that allows only orientation preserving. So if I combine conformal and anti-conformal maps, this is what I can actually get here. So in fact, this implies that these two are conformal or anti-conformal. So I will write in parentheses anti-conformal or anti-conformal. And the isometry group of HD is identified with this extended conformal group of SD minus 1, but the quasi-isometry group of HD, so it's like, I don't know, a lemma or proposition, right? So proposition is that the quasi-isometry group is identified with the group of quasi-conformal maps of SD minus 1. I will give a definition of quasi-conformal maps later. Okay. Yeah. Yes, we need to. Yeah, okay. yeah, here I should say that we identify, in fact, I should say something like that here, right? Equivalence classes of maps here, where equivalence classes contain maps of, so we collect bounded, yeah, indeed. Yeah, thank you. Yeah, we collect maps from like, okay, we collect maps with bounded distance, right? With bounded distance from each other in one class, right? Oh, sorry, with bounded, I missed the word. With bounded distance from each other in one class. Okay, so interestingly, quasi-isometries are quasi-conformal maps on the boundary. Another fun fact about quasi-isometries is actually the following. We're not going to use it, but still it's really worth mentioning. So there is this theorem which is called fundamental lemma of geometrical theory. Of geometrical theory, or Schwarzmüller lemma. If gamma acts geometrically, which means that properly discontinuously by isometries and co-compactly, compact by isometries, then in fact then gamma is finitely generated. It's finitely generated, and for any generating, so and for every finite generating set S, its Cayley graph with respect to S is quasi-isometric to the space X. Or one can think of the gamma being a metric space with respect to the word metric in this S, right? So I will say that or one can think of gamma with the word, okay, we equipped with the word, okay, one can think of gamma as of metric space with the word metric. With respect to S. Yeah. So simply it means that you have identity, right? Then the distance between the basically the distance between, I would say that the distance between G and GS is equal to 1, where S is an element of the generating set. Okay. So, and so on. So if you have some number of generating sets, you basically write every element of gamma is presented as some number of words, and this gives you basically the distance from the identity element to this element gamma, right? So you can then do this word metric, but this is basically the same as the Cayley graph. So the Cayley graph connects to points, to elements G and GS. Basically, you connect to elements of gamma by an edge, if and only if these two elements, so if one is obtained from another by multiplication on some generating element. So like basically the Cayley graph is some like visualization of the word metric. Okay, so this has a very interesting corollary, which I will state here. Corollary: all uniform hyperbolic lattices are quasi-isometric to each other, since they are quasi-isometric to each n. All uniform lattices gamma in zone G are quasi-isometric to each D and thus to each other. So in terms of geometric group theory, they are kind of the same. Well, again, it's not really true what I said, but in some like very, yeah, yes, indeed, on the very large scale, they are the same. Okay, so I think this is a good place to stop for today. So next time I'm going to say just a few words how to get this to the isometry, since this itself is a deep result, and in some kind of like geometric theory, one basically needs to use the Morse lemma to get this. Then we will talk a little bit about boundary maps and quasi-conformality. Quasi-conformality basically means that if you start with a disk on the sphere, the image of this disk is going to be generally from the ball on the sphere, the image is going to be an ellipsoid. And if this ellipsoid has, its eccentricity function of this ellipsoid is equal to 1, then this map is actually conformal. And this is what is killed by ergodic methods. See, but we first need differentiability. We need differentiability to use this ellipsoid thing, yeah, since we want this function to be pretty nice. And then basically here in this step, we will just use what was done in this second example. Right, let me show it just for a while, just for a minute. So this is essential that gamma acts ergodically on the boundary. And since it acts ergodically, we will be able to show that this parameter k is actually going to be constant almost everywhere. Since it will be invariant under gamma, it's going to be a measurable function. Due to ergodicity, we remember this formulation, right? Well, every function should be almost everywhere constant. Then we analyze two different cases. If it is 1 almost everywhere, it's already good. We proceed, but in fact, we should first show that it's not, it cannot be equal to any other constant. And then we use ergodicity again to eliminate every other constants from this. So yeah, overall, it's a pretty hard theorem, and well, it's beautiful. Okay, so yeah, thank you, and yeah, see you on Tuesday.